In this video, we're going to do a quick little introduction into the least squares regression line. So our story was that Chief-Roo was tracking her weight, mass in kilograms, over the last 20 months, and the number of times in the month she worked out. All right, so the days we've called our X, and her weight, her mass, we've called the Y. All right, so the mass was the Y, and the days were our X. All right, so she wanted to know about the association. And the logical thing is, once we have this graph, she wants to find the line through that graph of the data. And the line we're going to use is called a least squares regression line, or sometimes just regression line. All right, so here is the principle. We have our scatter plot. It looks like we have a nice little trend where our Y is decreasing as our X is increasing, right? Our weight is decreasing the more often we work out. And the line we want to draw is kind of through our data, but it's going to be some straight line. We usually do this Y equals mx plus b. M is our slope. We're going to call that b1 for reasons. And our intercept, we're going to call b0. Right now, our intercept is, if we had a 0 on this graph, that would be where our line would intersect where a 0. That's why it's called an intercept. It's intercepting our 0 or our y-axis if we had one. Right, and B1, our slope. This is our amount that y is going to change, right? Our change in the y for every change in our x, right? So that slope is the amount that y is changing every time I increase by 1 in x, right? Goes down, goes down, goes down, goes down, right? That's our slope. Having done the computation, here is our line. The idea is that we choose our b0 and our b1 from our equation so that, right, we find the vertical distance between every point and our theoretical line, and we choose b1 and b0 so that the squares of all of those distances, right, the sum of those squares are as small as possible, right? We want to make the sum of these squares small. And we call that the least squares line, the least of our squares. For us in this example, y is going to be 36.69, right? That would be our intercept. It's going to be about 36, minus 0.48x. And this slope and this intercept tell us something. So what does this line tell us? So the intercept, 36.69, it tells us if she does not work out, right? Our x is 0 days worked out. This model expects her weight to be 39.69 kilograms, right? That would be where our intersection would be. What the slope tells us, this minus 0.48, says that for every extra day she works out, right, for every increase in x by 1, the model predicts her weight is going to go down, right, that's the negative, drop or decrease, by 0.48 kilograms, right? So if she goes from 20 to 21 days, we would expect her weight, this drop, to be 0.48 kilograms. So that's what the slope and the intercept tell us in terms of this model. Now, as we see, the model isn't perfect, right? We have data points that are really high off the line. We have data points that are really low off the line. But in general, we can expect roughly 0.48 kilogram decrease every day of workout she adds per month. Clearly, there's going to be a limit. There's not that many days in the month.